Alright, time for another DrivePhysics.com, DebatePhysics.com video presentation. Alright, so the basic subject is there's lots of different tests you can do for energy. And the basic argument I'm making is that you have to choose kinetic energy or momentum to conserve. You can't conserve both. So if I do an experiment where I have the same mass in and the same mass out, alright, then I can conserve both. Because I can just make up any numbers and I'm going to get the same thing. Because it's the same mass. But any time an experiment involves a different mass, then you can't conserve both kinetic energy and momentum. One of them has to be sacrificed in every experiment. And I would argue that momentum is always going to give you a right answer, and kinetic energy will always get you the wrong answer. So with the lever, they're arguing that kinetic energy is conserved and that you can, in fact, use a lever to destroy momentum or make free momentum. That's what the argument is about. Okay, nobody will talk about the actual subject. And so I just want to make it clear that I know the actual subject. Okay, they don't. So I'm going to read the comments on Paul Nord's short. So even though it's a little bit obtuse in the sense that it's about a specific subject, a 1-minute video, and it's only loosely connected to Steve Mould's video, doesn't really get to the point of the conflict between whether levers conserve kinetic energy or whether levers conserve momentum. It's got 35,000 views, and I'd say it's a little bit strange just because it only has a purpose to somebody who's actually watched Steve Mould's video, realistically. But anyway, it is what it is. So there's quite a few comments, 30-something comments. So I figure it'd be worth going through some of those and just see how many are actually on this subject, which is Steve Mould's contention that levers conserve kinetic energy, and therefore, say for example, something half the mass can't go twice the velocity. So theoretically, you can't make an 8-pound bowling ball go an 8-pound bowling ball going 16 miles an hour isn't the same thing as a 16-pound ball going 8. Those kind of arguments that the simple argument is that somehow I can have a whole mass going 1 velocity and somehow I can't make a half mass go 2 velocity. It only goes 1.4. It loses 30% of the momentum somehow. Okay. So that's probably enough of a premise, and so let's see what we get here. Okay, he took a left turn and never got back to it. So, yeah. Who knows what that means? What he did was set up a fake premise that, okay, here's the law of the lever, here's what logic says that the half mass does go twice the velocity, and then he argues that somehow there's a proof somewhere that proves that it doesn't, even though there's no experimental evidence that proves it doesn't. And nobody's arguing that the experiment should actually be done, that this evidence should actually be created. So that's the ironic part, that no one's suggesting, why don't they do these experiments? And instead of talking about what they predict, why don't they actually test the predictions? I mean, what good are the predictions without the test? Okay, I mean, that's part of why I find this all so insipid. This process is that these people are science defenders and they don't know that the core of science is testing theories. You test them by doing experiments, and there's no experiments, ironically. All right, not everything that looks like a lever acts like a lever. You can't make anything out of that either. Okay, so what does that even mean? For example? Oh, no examples. So we're out of luck there. All right, I think it had more to do with the mass of the rods. So this was sort of an important thing to say, is that, well, if you're going to do the demonstration, you're going to point out somebody's wrong, you ought to do it clinically correct in the sense that there's no point in making two pendulums and then not having them the same length to do the comparison fairly. You want the lever to absorb the same amount of energy in both circumstances. You don't want to create a variable that could be blamed for the outcome. That's why the pulley setup they tried. So there's no pulley setup tried. There's no experimental data anywhere. So that just didn't happen. There's absolutely nothing. There's a drawing of a pulley. There's no pulley. But the point is the drawing was actually accurate and did point out that, the half mass does go twice the velocity. So it was exactly counter to what the video was arguing. So they used as a piece of evidence that basically proved the opposite theory, which, again, nobody caught it and said, that doesn't make any sense. How can you argue the 1.4 thing and then show a pulley doing the 2 thing? If it's doing the 2 thing, it's conserving momentum. How can pulleys conserve momentum and levers conserve kinetic energy? That doesn't make any sense. But no. Anyway, was better representation. Okay, so we have some responses to that. So, interestingly, we have the Dr. Julian Newman guy who made the insane mathematical video. But like I said, very impressive. I mean, the guy talked for 43 minutes, uninterrupted, without any defects in his voice, any hems or haws, or as if he was reading a script, and I don't think it was a script. I mean, it was, I think he's some kind of idiot savant or something. I mean, it was an incredible presentation, but it was absolute gibberish. Anyway, I think I had more to do with the mass of the rods. Okay, so that's the quote. And Dr. Julian says, why do you think that? Well, because it's obvious that part of the mass of the pendulum is the thing you're putting the masses on, and it's the center of mass of the pendulum that matters. So, yes, it's sort of important to use 2 sticks that are the same length. All right. Did the rod somehow look heavy? Yeah, extra. That's right. It was twice as long, which is, sort of a problem. That means it has more mass. The formula for moment of inertia gives that even under the assumption of the massless rod. Yeah, but we're not doing a massless rod. That's the whole point. The whole point is the reality isn't massless rods. Reality is you have to move the lever too. The lever absorbs energy to move. So it's taking some of the energy out of the experiment. You have to concede you're going to lose some energy to the movement of the lever itself. All right, having the attached mass while doubling the distance will have the overall effect of making it harder to achieve a given angular acceleration. So again, doesn't mean anything. Angular doesn't mean anything in these lever experiments, frankly. The angular part is irrelevant. Okay, because it's just twice the velocity. It doesn't matter that it's riding on a curved line. It's still twice the distance, twice the velocity. So it means nothing, frankly. It doesn't change anything. Angular momentum is momentum. It isn't angular momentum. It isn't some kind of special new kind of momentum. It's exactly the same rules. It's a mass moving a velocity, period. So this is more just jargon to hide the truth. The truth is you have to conserve the momentum. That's the truth here. The underlying truth is it should be a law of physics that momentum must be conserved. If you lose momentum in a system, you have to be able to explain where the momentum went. All right. So this is actually Paul's screen name. All right. Considering the angular acceleration, so again, this isn't really about acceleration, it's about velocities, but whatever, is a good insight. The whole idea of how the pendulum swings will be because it has a peak velocity. So you can just recognize that it really isn't about it's accelerating to a point. It's about the fact of what point does it accelerate to. What's its maximum velocity is all you need to know. Okay. And while these are not massless and perfectly rigid, they're not the same length, which is really important. You must, to eliminate it as a variable, The lever itself must be the same length, so you can just eliminate it as a distortion of the experiment. That's the point. The point is to have the same foundation. You can't do the two experiments. I can't have a scale and I'm going to measure stuff's weight, and then one scale has a rock on it and the other scale doesn't. That's going to corrupt the experiment. Okay. Ideal rods. They do demonstrate the general principle of two rods with differing masses, distributions having different periods when swung as pendulums. Yes, when allowed to oscillate by gravity. Okay, but that's not what we're really talking about here with a lever. We're talking about an applied force by a human being. That means a human being can make something move really fast in gravity or really slow. It can move at any speed in gravity. It doesn't have to do the free fall speed, and it doesn't have to worry about, well, if I want to just use a minimum amount of energy, I shoot something at twice the velocity and it will stop at 4 times the distance. Well, I could shoot it at 10 times the velocity and still have it land there because I could put the brakes on. You know, humans can brake, so they can do things faster. So it's very different. And so you have to account for the actual momentum of the actual action you're doing to the lever. You're not doing it based on free fall velocity or shooting or launching velocities. You're doing it based on human applying a force velocity. But anyway. All right, so then the doctor replies. Oh, probably too much. Yes, indeed. Your demonstration, the rods nicely illustrate how different masses, distributions in a pendulum lead to different periods, even despite the rods not being perfectly ideal, rigid, weightless rods. So look, the problem is when you allow gravity to move them as a pendulum or an oscillator, then gravity is going to move them at gravitational speed, okay, based on the fact that you're placing a mass on one side of the lever or the other side of the lever as it oscillates, and it's only going to be able to move that mass at gravitational speeds, not human speeds or not some other outside forces speeds. So it's going to oscillate in the gravity, okay. So then the total mass on the lever matters, but it doesn't change the fact that the momentum of the lever is the same. All right. Please note, however, that the experiment in Steve's video, which doesn't really have much to do with this, it was just his poor demonstration where they were going to test whether you could tell the difference between the half mass and the full mass. Half mass, twice the distance. The law of the lever basically says, Archimedes would say, that moving the half mass is the same energy as moving the full mass a distance closer. And you're not going to be able to tell the difference. Same force applied to move them. Please note, however, that the experiment in Steve Mould's video does not illustrate a principle about pendulums' periods. Right, it really wasn't the point of the video. But rather a principle about levers. Yes, a principle about whether they conserve kinetic energy or they conserve momentum, because the two can't both be conserved. It's not possible in the scenario described because of the change in the mass. If you change the mass in an experiment and you're going to convert energy from a heavy thing to a light thing or from a light thing to a heavy thing, you cannot ever conserve both kinetic energy and momentum. You have to sacrifice one of them. See my reply to your comment underneath my comment. Thanks. I don't know. I don't think I'll find that, but okay. All right, YouTube Observer. Steve has the rods the same length. Yes, he does, even though he doesn't draw them the same length, which is also a problem. Deceptive. Okay, pointlessly, these are errors that we all shouldn't make. I make them, we all make them, but we shouldn't make them because they create possibility for these kinds of tangential arguments. It all should be as precise as possible, which is going to affect the pendulum as mass of the rods also in play. So clearly the mass of the rods matters. The mass of the lever matters in an experiment. If I make the lever out of lead, okay, it's going to behave quite differently in terms of how much energy it's going to absorb, and therefore you're not going to be able to do these experiments. I drop a tomato on a 4,000-pound lead lever. It's not going anywhere. It's not going to demonstrate anything. However, to the same extent, both videos have problematic parts which fall into account for the various configurations. They're obviously, the argument is problematic in the sense that you're saying, look, I'm going to create free momentum or I'm going to destroy momentum. And the vice versa is I'm going to create free kinetic energy or I'm going to destroy kinetic energy. The problem is only one of these stupid theories can be an actual description of reality in terms of what is energy. They both can't be real things. And I'm arguing that momentum was here first, and it was right. It works really, really well, always. Kinetic energy works really, really badly, always. All right, it is not a thing about pendulums that... It is not the thing about pendulums that the mass is not part of the equation for frequency. That mass is not part of the equation for frequency. Well, it certainly is when you have a mass, a stick, that has masses in different positions. So if the stick isn't regular, that is, if the pendulum isn't a bob at the end of a string, it's certainly going to matter because it's not evenly distributed. The assumption is when the mass is at the bottom of the spring, the center of mass is fixed. But if I have a piece of wood that, has heavy parts and thin parts, I'm going to get a different answer. It's not going to matter how long it is. It's going to matter where the center of the mass is. So it does matter. Okay. So this guy says, Paul says, that's a small perturbation to the experiment. Assume that they are massless and perfectly rigid physics rods. So again, let's not do that. Let's actually do the experiment with real things in the real universe and see how it actually works. Let's not keep pretending that we can make idealizations. Now, we can never test the gun recoil and the bullet, right? We're never going to make a lever that can test that. But we can make some other device that might be able to. All right. They will still have different periods. Okay. All right. So this is... So he's responding to something else, I guess. He says something more. He says, excellent observation about the period being dependent only on the length. So it's not dependent on only the length. That's just wrong. At the same time, the amount of force required to set it in motion will depend on the mass. Exactly. Let's see. And how much mass will define how much momentum it has. So the fact that it's oscillating, two things can oscillate at the same speed and have very different amounts of momentum. Let's see, that's the feedback that Steve is noticing. So there's some kind of feedback that Steve is noticing. Oh, okay, that's the bouncing. So the bouncing just means that you're putting force in at like 500 miles an hour, and the only speed it can rebound at is the gravitational free fall weight. It can't fall faster than free fall, obviously. It can't do any of this stuff. Gravity can't have it can't respond in kind. It has to just say, okay, it's 4 times higher, I will, so you could have got it 4 times higher by making it go there in a split second. It still has to drop back down at the rate gravity is going to drop that mass, and that's always fixed. So you can't change that part of it. So yes, it's theoretically you can dissect the truth about which mass is on the lever if you allow gravity to give you an indication. But if you're really holding and you're always applying the force, you're always applying the momentum to the object, you won't be able to tell. That's the tactile feedback that Steve was noticing. And the fact that the pendulums responded differently to the same input shows that. So they're technically not supposed to be pendulums. They're supposed to be something you have control of, and you're seeing how much energy it takes to move a mass. You're applying all the force. There's no gravity involved. That's the whole point. So clearly we're back to, well, maybe we have to rotate things horizontally to get out of any notion that gravity is some kind of a relevant feature. So we need to go to some kind of object where you take gravity out of as a variable. Gravity won't be a variable anymore. All right. What you failed to mention is that it's not just the length, but also the mass that demonstrates the mode the pendulum swings. So clearly, yes, that was missing here. Is that the simple argument is that if you're going to make a lever with masses that are scalable, that is, you can move them to different positions, then you have to concede that it's the center of mass that's going to control. All right, so this guy says, mass has no effect if you consider it happens in isolated systems. You mean gravitational acceleration. So no, he doesn't, but whatever. No, he means the center of mass. So again, traditional pendulums are things held from strings. And so they have a very regular center of mass. There's, because it's almost a nothing. There's no distribution of the mass in some kind of irregular way, because the string is almost irrelevant as a thing. And you're just saying the center of mass is the distance times the rest of the mass, and so it's a string, so the center of mass is, you could argue, is at the location where the bob is, because that's all the mass is in that one position. Obviously, if you're using sticks, you have mass in lots of positions. Since gravity acts in direct proportion to the mass, it doesn't matter how much a pendulum weighs. It does matter how the weight is distributed. So again, if I'm moving the weight on the pendulum, I will change how fast the pendulum moves. So again, this is like one of those timers for a piano or something. Those music things that go back and forth. They have a little stick on, a little stick, and you can just move the weight up and down and change how fast it oscillates. So obviously it matters where the center of the mass is. All right, its period is determined only by the distance between the pivot and the center of mass. Well, there you go. So the center of mass for a stick is different than the center of mass for a string or a steel bar or some other thing that has a constant mass, a constant distribution of mass. All right. Sorry. Yeah, this video isn't for everybody. I should have said that at the beginning. Sorry, if you've been listening this long, I don't intend everybody to find this all incredibly interesting. I just thought it was worthwhile. People posted the comments, and might as well respond to them. Comparing time intervals shows time exists, not in illusions. So that's not even a good sentence. Comparing time intervals shows time exists, not in illusions. Question mark. Whatever. Okay, no, it's moment of inertia. So this guy says, no, it's moment of inertia. See compound pendulums. So compound pendulums don't change anything, as Galileo pointed out. It's still just adding up the distances times the mass, and the distances are the velocities. It's all mv. Plus the length vs, inertia distinction is just by rearranging the formula. Some sort of smiley thing. Yes, that's the test that Steve is using. So what test? There's no test. Okay, so again, just bullshit again. Mainly it all shows how much complexity is hidden in the mechanical dynamic system in the modern electronic software folks miss. All good thinking material. I don't know what the hell that is. Completely off subject. Yeah, brilliant. The video short wasn't able to explain all these details. Exactly. So, just a bad idea to make physics arguments in shorts. It's just asking for trouble. A physical pendulum will have its period determined by the distance between the pivot and the center of mass. So, again, this is generally true for small angles, but point about two different pendulums having different periods remains, and that was Steve's test. Well, it also should be pointed out that the small angle thing is the truth. So once you start put more and more energy into the system, all of a sudden it breaks down. These rules aren't as consistent, which is interesting. That might mean that wind resistance or something else is playing more of a part. Who knows? Great demonstration. I hope Steve replies. Well, so far, not so much. Whoops, I don't want that. Damn. It's playing the other fucking piece of shit. Oh, fuck, I hate shorts.
I wanted to give a quick reply to Steve
I hate
Mould's
shorts.
confusion about...
No, shut up. Sorry, but I hate shorts. I like wearing shorts, don't like watching them. Let's see. I think he had more mass in the rods. That's why. Okay, not everything looks like. Okay, we already did that. We did that. No, it's a moment of inertia. Great demonstration. Hope Steve replies. There we go. But can't work out what this video is demonstrating. Okay, so this is Dr. Julian Newman. Obviously, his video, Steve's video, was demonstrating kinetic energy somehow wins the debate. And this video was just pointing out how one of the really bad demonstrations that Steve Mould did was just that. It was just a really bad demonstration. Let's see. You say you hope Steve replies, but if I was Steve Mould's position, I wouldn't know what to reply. It sounds like this video is trying to demonstrate some kind of error in Steve Mould's video. Yes, the error was in his testing method. So they're trying to test whether you can feel the difference between a 1 mass twice the distance and a 2 mass 1 distance. And the law of the lever says, nah, basically you can't tell the difference because it's the same momentum you have to produce. The same momentum will feel like the same momentum, okay? The same weight feels like the same weight. 4 pounds feels like 4 pounds. You can't make 4 pounds feel like 10 pounds. So, but he did a terrible test because of the way he built his device, his wobbly pendulum device. I wouldn't know what to reply. Sounds like this video is just trying to demonstrate Steve Mould's. Okay, but the point in Steve's video is essentially just that varying the mass and the distance from the fulcrum in a way that keeps their product the same won't keep the rotational inertia the same. So whatever that means, the rotational inertia, again, arguing that somehow light things resist being pushed at higher velocities. That somehow, okay, you put in the fat lady on one side of the lever and you can't lift 2 thin ladies on the other side, kind of argument. And of course you can. And this is centuries old standard knowledge. So again, this is the part that's just irrational. To argue about some kind of centuries old knowledge that has anything to do with something other than conserving momentum. That's the part that's centuries old. I mean, it's millennia old. Okay, that you can find in high school mechanics test books without any good evidence supporting it, by the way. Just look up moment of inertia on Wikipedia. I have dissected the nonsense page, and it's just that nonsense. There's no such thing as any moment of inertia. Okay, so he says, I hope so too, whatever that means. Okay, okay, responds to the video. Yeah, he's not going to respond. Cool video, thanks. Yeah, that was really worth it. Not quite sure you understand what Steve was trying to say with that experiment. So again, it's just, he was trying to say that somehow you could tell the difference between, if I have a perfect balance, okay, and I balance the 4 mass and the 1 mass, and they're at the different lengths, and the balance says they weigh the same thing, their argument is they don't. That is, you could figure out which one weighs 4 pounds and which one weighs 1 pound at 4 distance. Even though the scale says they weigh the same, they have the same momentum, you can tell the difference. And no, you can't. Why too many people try to solve this type of problem looking at forces only instead of starting from conservation of energy? So conservation of energy means nothing, because it's really conservation of momentum versus conservation of kinetic energy. And so every time somebody says conservation of energy, they're implying it could be momentum he's talking about, right? Because most people don't make these distinctions. That is the reason Steve made the wrong explanation of how the torpedo works, and also how Derek made a completely wrong explanation of the direct downwind faster than wind cart. So yes, I'll agree that Veritasium's wind explanation was silly, and especially considering he was in the car and actually drove it and actually used the lever that changes the pitch on the propeller blades. So you go from having a flywheel that's just a flat sail to having a propeller. And that was the whole trick, is that when it's a flywheel, it's not doing any damage. And then when you turn it into a fan, that's when it's going to add energy. Okay, I think you are correct. The critique here is only of the pendulum swinging test. He needed to consider the momentum and energy conservation of both sides of the lever. The constant force rocket can't have any work done on it because it has no mass. So again, that I don't even understand why they're playing that game, that somehow the rocket or the thing you're using to create a constant force is somehow some sort of idealization. Why is it an idealization? Why don't we just say it's a rock thrown? It has a mass and a velocity. It has a momentum. It's going to hit the lever with that momentum. Now let's see what happens. Okay, if he had considered a source of force that has some mass of its own, I don't think it was a massless rocket, but who cares? The energy and momentum equations would have balanced. So this is the assertion that I'm arguing is nonsense. I don't know why a physicist would say it. There's no way to figure it. How can mv squared equal mv? It's just not possible that you could have consistent answers. I mean, you're squaring the velocity, you're changing the mass, changing the velocity. How can you conserve both? It's impossible to conserve both. If I change the mass, it's impossible to conserve both of those substances, kinetic energy and momentum. It's never possible. I mean, gun, bullet, right? You fire the gun and the bullet. Well, the kinetic energy says there's 2,000 joules going one way and 2 joules going the other way. Momentum says, yeah, there's 2 joules going that way and 2 joules going that way. They're obviously not equal or conserving. It can't be possible. The momentum's conserved. The kinetic energy is way the hell out of whack. Let's just say the momentum is balanced. We don't have to use the word conservation. We can just say the momentum's balanced. Clearly, kinetic energy is hugely imbalanced. It's just that Newton's third law implies that the kinetic energy should be balanced. If that's real energy, it should be obeying the third law. So this guy says friends. I don't know what that means. With Steve? ? Of course. I've had occasion to be part of a workshop with him. Oh, they're going on an ocean cruise now. So that's the new Steve Mould video. Now he's put up another short selling tickets to some boat ride. And you're just like, oh, fuck. It's some meet and greet bullshit. And we've exchanged a few emails. I hope I don't seem disrespectful. Well, maybe you should send him another email. Maybe you should say, why don't you actually test this, Steve? Why don't we actually do the experiment? Wouldn't that be a marvelous thing to do? Take that high-speed camera and put it on that lever and see if the lever moves in some different way. That would be spectacularly insightful and useful. But no, they won't do that. All right, with all due respect, your video here about Steve Mould's confusion is, at best, very confusing and potentially misleading. You haven't made entirely clear what you're trying to illustrate in the first part of your video. Yeah, it's a 1-minute video, so yeah, I don't think it's going to be, it's going to be making a clear point. Oh, look at all this crap. Oh, this is the doctor again. So this is Julian. But if you're trying to suggest that Steve was wrong in stating that it takes less force applied at a given distance from the pivot to achieve a given angular acceleration when you double the mass and have the mass's distance from the pivot, then it is you that is mistaken. So he's saying if you think, but if you're trying to suggest that it takes less mass, that Steve Mould was wrong in stating that it takes less force. Okay, so again, it somehow takes less force to move a 2 mass 1 velocity than it takes to move a one mass two velocity. That's their argument. That Newton's third law really is rubbish, and the second law might as well be called rubbish too. Yeah, because it's not twice the force, twice the velocity, three times the force, three times the velocity. They're contending it's something completely different. All right, a one-line moment of inertia calculation allows that Steve Mould's assertion is correct. So let's just recognize that didn't happen. So he made a 45-minute video doing calculations, and all he did really was, here's momentum calculated, and now I'm just going to change the formula and put a squared radius in. So yeah, I'm just going to add a squared function, and now I'm going to say that's proven, when no, it's not proven. I'm also having trouble understanding what you're getting at in the second half of the video. There's a second half to the 1 minute video? Anyway, the effect of having a vertical orientation in Steve Mould's video, what you're calling as a pendulum, is that the force of gravity has no turning moment. I don't know what that means. Of course it does, but whatever. I'm sure it does. If you're saying it doesn't, I'm sure it does. And so only the rotational inertia. So no such thing as rotational inertia. There's no matter resists being moved. You just have to give it energy and it moves. If you don't give it energy, it doesn't move. You give it energy, it moves. It's just absolute nonsense that there's anything called an inertia. It has no turning moment. And so only the rotational inertia enters into how the applied forces translate into angular acceleration. So again, the angular acceleration is the same as regular acceleration. It's the same thing. It's just momentum. That's all there ever is. Of course, it's true that as soon as the applied force causes the orientation to stop being perfectly vertical, gravity does then provide the turning moment, which I guess is what your pendulum point is meant to be concerned with. Right, so you're wrong to be so critical, because yes, he is pointing out that if you jiggle something in gravity, well, then you might be able to detect that your energy isn't the only energy playing with the system, that gravity will be playing back. All right, well, anyway, this is all more than I wanted to read. Of course, it's true that as soon as you applied force, okay, provide turning moment. Okay, but that turning moment is a higher order term. So he claims it's a higher order term. It's not a higher order term. So he's just claiming that somehow light things are harder to push because he says so. Okay, compared to the phenomenon that Steve Mould is interested in. So again, he's not very interested. Steve Mould isn't very interested because he didn't do the stinking experiment. So he won't make a lever and prove his point. In other words, the reason why people experience the one vertical lever to be easier to wiggle about is that the other vertical lever is precisely because the phenomenon that Steve Mould's video was about. What phenomena? Conservation of kinetic energy, 1.4. That's not a phenomenon. That's an accusation. That's an assertion. That's not a tested phenomenon. And not because of anything to do with the effect of gravity on those levers. Yes, if you're just pushing and you're maintaining control, if you bounce things, okay, then gravity is going to be in control in terms of bringing them back to the lever. All right, let's see. Didn't learn anything, thanks, though. Well, that's useful. Oh, here's another stinking reply. Let's see. The video short is difficult format to say anything completely. Right, you chose it. Okay, you could have made a real video, but you didn't. It's a critique merely of the pendulum test that Steve used to see if levers with masses at different distance behave differently. The better critique is that he forgot to consider the time it takes for the two levers to interact. So again, you can do these experiments with a horizontal lever and just eliminate all of this mush about what gravity's doing. All right, the 0.5 kilogram mass at 2 meters will experience half the force. So here we go. Okay, that the 1 kilogram mass at 1 meter will feel. So it's just, again, he's just arguing that somehow this is about a constant force being applied over a constant distance or some other mush, and really it's just about achieving a velocity, a momentum. and we can probably give it that momentum in an instant. There's no acceleration that's meaningful. The amount of time it's accelerating is almost zero compared to the amount of time it will be moving with the energy we give it. All right, that just means that they will experience the same acceleration. So he's arguing that if they're experiencing the same acceleration and one's doing it for twice the distance, then it's going to go twice as fast. So again, wrong. Anyway, but in the interaction, the 5 kilogram mass will move 2 meters while the 1 kilogram mass moves 1 meter. Well, if you see, now he's saying it's going to go twice as fast. So, you know, this is just kind of duplicitous, right? I mean, he's arguing with me, defending the 1.4 thing, and now he's conceding in his own comments section that, no, there's no 1.4 thing. It's going to be going twice as fast. Nothing you can do with this. The rocket in Steve's illustration will have to operate longer in the case of the 0.5 kilogram mass. So obviously it can't operate longer and move the lever slower, because then it's not going to leave faster. So this whole argument that the rocket goes longer, the lever moves identically when it moves twice. When the half mass moves twice the velocity, the lever will move identical to how it moved with the 2 mass. So there's no rocket faster thing possible. And if I make the rocket move faster or slower, if I make the rocket move slower, it means the lever has to move slower, which means the object moves slower, which means you've lost the energy. You put more energy in and, you know, more force for a longer period of time, and somehow, you know, the equal same force for a longer period of time, and somehow come out with even less energy. That can't happen. All right, if he had modeled a real rocket, oh brother, it might have been obvious that the rate of mass ejected from the rocket carries an extra momentum that he failed to consider. So again, the argument is the law of the lever basically says the lever moves exactly the same in both circumstances. All right. So then the doctor comes back with, let's see how much this is. Oh, I don't think we'll do this. Well, we'll do a little bit. But the pendulum test, can you still see any of this crap? Well, almost. It's almost off the screen, actually. Oh, yeah, it's a thread. Okay, so that's why it's way over there. All right. But the pendulum test, to use your term that Steve used, correctly illustrates that levers behave differently. No, they don't. But greater mass, shorter beam is easier to wiggle. So now he's again arguing that it's easier to move the heavy mass 1 velocity than it is to move the half mass twice the velocity. And I'm saying it's obviously nothing defending that nonsense. All right, he says down here, if not, then your communication was incoherent and it is impossible to guess what you meant. But I think you were communicating coherently in that sentence and communicating something untrue. Yeah, I guess so. And if I push them in the same with the same force. Yeah, there's no point in getting into the force argument. In conclusion, if you're going to make a public video claiming to respond to a science communicator's confusion, I respectfully think you should be more careful to check your own understanding first. So that seems a little snarky that he gets away with this stuff. So I can't say anything that's snarky and get away with it. People get all butthurt and run away. You say the video short is a difficult format to say anything completely, but I think that if you had more time in your video to explain, you would have just made it less ambiguous and more clear that you're misunderstood the physics going on here. Well, again, that's the whole problem, right? I can't nail them down. Is it 1.4 or is it 2.0? Pulleys are 2.0. Pulleys conserve momentum. You're arguing that levers don't. Okay, explain, please. I don't understand how that's possible. P.S. Regarding, he forgot to consider the time it takes for the two levers to interact. Is this what gets addressed at blah, blah, blah of the video? So it's like milliseconds of the video. I don't think I'll bother with that. All right. Didn't learn anything, thanks, though. Okay, let's see what the response was. That's okay, maybe next time. Oh, brother. All right. It's because the pendulum works off gravity, which is constant, and the length difference means no one has to cover more distance than the other with the same force, so it takes longer to complete its arc. So the very point is that if you're letting gravity affect it, it's going to have one. It can only collect so much energy from the gravity. If you're moving it, it can be any amount of energy you choose to put into it, any amount of velocity, and that you can move it at 50 miles an hour and make it stop almost instantly. So, I mean, you don't have to worry about it continuing in some arc and that it's going to go all the way up in gravity and then come back down. If I move it 50 miles an hour to 1 inch above the ground, it's not coming back at 50 miles an hour. Okay, gravity's not going to be able to produce the same effect I put in. It's going to produce its regular amount of gravity effect. It's not going to have any way of knowing that I actually moved it at 50 miles an hour to bring it to this point, and then I stopped it, and now it's going to fall in gravity. All it's going to be, gravity's going to do is bring back the fall rate. It's not going to go 50 miles an hour back down. I mean, all of this is nuanced, and but the experiment would clear up all the nuance. If we had the experimental information, then all the nuance goes away. All this bullshit argument goes away. I'm not saying you can't analyze the experiment. I'm just saying it would tell you what the actual outcome is, which would be a huge advantage in this conversation, would be to know what it actually does when you do the experiment. And nobody will defend. Not a single person says, why don't we do this experiment very well and see what actually happens? Not a single person says, let's do the experiment. Let's get Steve Mould to use his high-speed camera and his other tools and actually do the experiment. No, nobody's saying that. All right, anyway, so 3 replies. Did I open all of them? Yeah. That's also true of Steve's rocket animation. So we went back to the stupid animation. It's just a force going in. You're supposed to assume it's constant. You just think of it as a baseball. Why are we, this shouldn't be that complicated. So then as soon as somebody says F equals ma, I know bullshit's coming. Means that the 1 kilogram mass will experience a 1 Newton force and the 1/2 will experience a 1/2 Newton force. The acceleration will be the same for both. So again, he's saying it's still saying the same thing, that somehow it goes off with twice the velocity when he's arguing with me that it's 1.4. But the distance they traveled will be different. Well, obviously it's twice the distance, yeah, with the same acceleration. The one that moves the longer distance will take longer to accelerate. So just more nonsense. That's duh. But the acceleration, again, when a human being is doing it, is going to be a tiny amount of time. It's not going to be a relevant part of the lever experience. So he says, well said. Okay, I love this sort of stuff about physics. So at least this guy likes that somebody might argue something once in a while. So few that do that. Now, for some reason that I don't really understand, I didn't post the first comment. I posted like the 6th or 7th comment, and mine is at the bottom. Yeah, seems kind of like, oh, gee, isn't this shenanigan? My comment is on the bottom. Oh, I did again. Oh, fuck these. I hate shorts.
I wanted to give a quick reply to Steve
shorts.
Mould.
I hate shorts. I hate shorts. Anyway, okay. So, enough of a video. Don't know when I'll post this. Maybe I will save it as a Steve Mould video just because it is on the subject and it's just not going to be very exciting. But anyway, I think that's enough, right? How much time is it? 49. I probably could draw the lever again, right? I mean, who's watching this video? Nobody's watching this, right? So, all the way through, what's the odds? And the only person that might be doing it is somebody interested in the subject, and they might be saying, what are you even talking about? I didn't see any of this, so I don't even know what you're talking about. So I might as well, just for the benefit of that person, that one person, see how considerate I am, that I'll do things for just one person. I'll just help the one person. All right, so again, the simple argument is that if you set up a lever, now that's set up horizontally, okay, so then we're going to get rid of gravity. And we're going to just have a really good bearing. So it's not going to matter that one lever might weigh 5 pounds and one lever might weigh 2 pounds. Not going to make any difference because we have a nice little bearing. All right, what do I have to do here? I have to fix this fact that, yeah, well, which one is that? Oh, I have to remember. Okay, this is what I have to fix. Yeah, pretty sure. No, that's not it, you asshole. This is what I have to fix. All right. So the idea is that you're gonna, so let's just say we're looking at from the top now, and the idea is like I said, this experiment has been done. So I could put a spring on here and then completely control how things are launched. And the simple argument is you're just saying you're going to take a 1 mass and a half mass in these 2 locations and do these experiments. Now, you could say that if I was to feel how much pressure or resistance something was making, I can also do it in reverse, right? Because the shorter distance will be harder to pull here, and it'll be easier to pull here, but I'll have to pull it for a further distance. And the opposite statement is that if I'm on this side of the lever and there's no spring here and I'm just going to push on it, the fact is it's the same. To give this momentum is the same as to give this momentum, in the sense that it's just momentum. So I'm going to put a certain momentum in. I have every expectation that it's going to feel the same when I'm taking the 1 mass going 1 velocity is going to feel the same as the half mass, going 2 velocity. It's going to feel the same. It's the same momentum. It's the same weight. They're basically saying it's the same weight. If I put a weight here, a 2 mass, this is the same weight, and this is the same weight. This weight is the same for both of these objects. It balances both of them, no problem. And then it oscillates with both of them, no problem. So they have to feel the same, theoretically. They can't feel different because the test is saying they weigh the same thing. I can't put a frog on a scale and it has a weight, and then I take a mouse and put it on the scale and it has a weight, and they both weigh exactly the same, and then say, okay, if I have the frog in one hand and the mouse in the other hand, I can feel the difference. How can I feel the difference? They weigh exactly the same. So, that's the core of the argument. So their argument is that somehow the lighter thing is harder to push because we have to conserve kinetic energy, and somehow it fails to go 2 velocity. So the 1 mass, or no, we'll say that's a 2 mass, the 1 mass won't go 2 velocity. So we won't have this relationship anymore. Somehow it breaks down and we can't move the 1 mass 2 velocity. It can only go 1.4, and we have to lose 30% of the momentum. And then if we reverse the experiment and instead put the 1 mass going 1.4 in this side, somehow we will be able to launch the 2 mass at 1 velocity, and therefore plus 30% momentum. So we'll have a free momentum machine we can make. And so we can just make these masses more and more extreme, a 1 mass and an 8 mass, some kind of extremes, and I can increase this 30% to who knows how much. And I can just keep making lots of free momentum, which doesn't happen in reality. Ever. Can't make free momentum. All right. So, enough said, and I've got to find my mouse. So many things to do, so much to get done, blah, 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 and you have to do this. So many good subjects in physics, and if we can't get past this one, there's just no point talking about any others, but this one is so basic and so simple. If people will fail to accept the truth here, they're going to fail to accept the truth anywhere else and everywhere else. Right, so till the next time and such. That really is enough. Alright, just a little add-on. So I have received a couple of comments that are referencing the insanely amateur experiments done by people. I guess they're people. I don't know. just cranks. They're my haters. People who hate me. You know, they used to like me and then they hate me because I hurt their feelings in some way. And so they have to defeat me. Blah, blah, blah. And that's all it's about. And so they contrive experiments and they don't account for all kinds of variables and they make a mess. And then they don't even retract it once it's been clearly pointed out they made an error, like something obvious, like measuring wrong on the ruler or something, and they still won't claim, okay, that's not a good video, I'll take that down. They still won't admit that their propaganda is just that, lies and propaganda. And so I've debunked dozens of these crappy experiments. And so the example would be, you know, they'll do the crashing of the objects into each other, and they'll do it with something that's 5 inches. So a pendulum of 5 inches. So it's this little tiny thing. And then they're going to try to film it and then try to do frame rates on it. Okay. And so it's like using Maxbox cars, is that what they're called? You know, and then saying this is duplicating real car crashes and stuff. I mean, the room for error and you know, the margin of error just becomes huge when you're trying to do these little rickety experiments. Even the weight of the string you're dangling the objects by becomes more and more relevant. So if you want to do the experiment right, you do it as big as possible. Newton did it from like 12 feet. Okay, so he made pendulums that were 12 feet long, 12 feet high. All right, because it slows everything down. Okay, you're using bigger masses. You can really see what's happening so much better. All right, and the fact is, if you're going to film it, you don't film it from way back here. Okay, and you have little things going like this in front of you. No, you put your camera as close as possible to the collision and try to just get a really good video of the collision. But they don't do that. Okay, and they don't worry about what angle they're viewing it at. So they'll take an experiment that's happening this way and they'll turn it this way, and just so they get a view this way, you know, so you're not really seeing the actual distances. So all kinds of cheats and manipulations and bullshit to sit there and try to prove a point. And then they don't even go the step further. Like, let's just say you did the experiment. I mean, I did do it, so they'll just point out that you know, I did it with pieces of steel, okay, and I did have a little compression spring, bent metal spring. And, you know, 1 mass against a 3 mass. I guess it was a 2 mass at that time. Yeah, it might have been just the 2. You know, and I did it from 5 feet, okay, heavy steel, rebar. You know, the problem I had was that, you know, they would turn, you know, because it's steel, it's, you know, it's on, it's, so when it hits, it would leave at an angle, and that would ruin your video, being able to measure frame rates, because it's turning as it's moving and changing its size, which doesn't help any. But anyway, so I did do it, and it's, like I said, I didn't get any of these numbers that they're getting. But regardless, there's all kinds of ways you do it. And then if you did actually get this phenomenon to happen, where you did a 1 to 3 and you actually got an increase in momentum, you know, so you went from 100 in and you got 150 out, well, then your next logical step is to say, okay, well, let's try it with something 6 times as heavy, you know, and see if we can get the full 200, you know, and the full 100 back, because then we're really in business with our perpetual motion machine. So if you're going to argue that you can make free momentum, well, yeah, the next logical step is to take it to its maximum. See how much free momentum you could actually make. You know, because obviously I would argue that as soon as you can do that, then I would just feed, okay, extra weights into this position, and you could just keep knocking them out of here all day long. You could just keep banging things out with twice the momentum, twice the momentum, twice the momentum. You know, and so you can convert a tiny movement into a gigantic amount of movement. But they don't do any of that to increase their credibility in making these arguments. They don't debunk the fact that their theory predicts a perpetual motion machine. They don't have any counter argument for that at all, because that's absolutely what it does predict. So again, this is where we're all the way back to, professional bowlers use 16-pound bowling balls. They don't use 8-pound bowling balls because, lighter balls don't have more energy. yeah. Smaller isn't better. Yeah. So it is just bullshit. And I'm not going to deal with comments, all right? I already made dozens of videos debunking their crappy experiments, and I explained that I don't have that obligation, and I want good experiments. So the very fact that these people think this is what should decide what we believe, right? Matchbook car experiments, little dinky, experiments, those should decide what people believe. It's essentially just endorsing religion, voodoo, Sasquatchian science, UFO science. So it's just they're going to sacrifice good science on the altar of their hatred for me, and that's all they're doing. So I'm not going to give them a voice. So if you're going to bring up these shitty experiments that I've debunked over and over again, that they haven't taken down, okay, and they leave up as just glaring propaganda, lies. They're just lies. It's lie science. When they say some experiment proves something and it absolutely doesn't prove it because they did it wrong, that's lying. Okay, and that's all they're about, is the propaganda. So post a comment referencing it, you're blocked. That's simple. I'm not playing. Okay, so fuck you. If you think that's good science, that's your opinion. I think it's idiotic. I think you're a dupe and a fool, and it will be eventually proven when these experiments are actually done clinically well. So that will be the moment. And what is going to be your penance for being an advocate for the bad science? When the truth is revealed, what are you going to do? Because you're just going to have to admit that you are evil and stupid, and you didn't do any of this for any good reason. So you're just going to have to admit that you tried to corrupt science. That's going to be on your tombstone. So live with that, asshole. Assholes. Okay. Yeah. All right. So, till the next time and such. The whole point is that we're looking for evidence. But there's no point in getting evidence that's of a lower quality than the evidence that already exists. Again, the Mythbusters isn't perfect. Far from it. But it's a hell of a lot better than these crappy experiments. And it proves otherwise.